When a physical robot attempts to execute a geometrically optimal path generated by a standard A-star search, the results are often highly destructive. The mathematical route is valid, but sharp 90-degree angles demand instantaneous heading changes, forcing the robot to violently stutter, stop, and overshoot the corners. This graphic compares two different approaches to solving that problem. On the right, the smooth red trajectory cleanly navigates the obstacles without oscillation, representing a fully integrated path smoothing and predictive control pipeline. A path planning algorithm that finds a mathematically valid route to a goal does not mean a robot's physical actuators can actually drive it. By combining an A-star search with line-of-sight pruning, continuous curvature smoothing, and tuned motion control, we can reduce trajectory tracking errors by 48% and cut peak maximum deviation by 62%. To understand exactly how those performance gains are achieved, we have to trace this pipeline backward. We will start with the physical execution, move through trajectory smoothing, and finish at the initial graph search. Achieving optimal navigation requires bridging the discrete search space of a digital Mac with the continuous kinematic constraints of real hardware. At the very front end of any navigation pipeline is the path planner. In known structured environments where a robot repeatedly travels between fixed points, calculating a full grid search from scratch for every single trip consumes vital processing power. This map breakdown illustrates a dynamic memory-based retrieval system. By identifying static obstacles, the algorithm divides the free space into discrete, multicolored convex cells. The system then calculates and caches optimal path segments between these adjacent regions. This comparison reveals the efficiency gain. On the left, a standard search expands a massive scatter of gray nodes to find the route. On the right, the memory system simply connects the cached path segments, ignoring the vast majority of the grid. This retrieval drops mean computation time from 12.1 down to just 1.3 milliseconds. This happens because the system no longer executes an active logarithmic graph search. Finding a route becomes a near-constant time operation, requiring only a quick cell lookup and the concatenation of known coordinates. That 9.3 times speedup shifts the initial planning phase entirely from active search to passive retrieval. This frees up the tight computational budget required for the next mathematically demanding step, dynamic trajectory smoothing. Even the most efficient memory retrieval system still outputs pruned waypoints connected by straight lines. The resulting path contains sharp vertices, which act as strict kinematic discontinuities for the machine. An instantaneous change in heading at a sharp vertex demands infinite centripetal acceleration. A physical motor cannot deliver infinite torque, so the robot must either fully stop and pivot or skid off the path. This graphic demonstrates the solution. The pipeline takes the sharp, linear waypoints on the left and passes them through a B-spline generator, producing the rounded, continuous trajectory on the right. The discrete waypoints act as control points to shape a continuous polynomial curve. This enforces C2 continuity, meaning curvature changes smoothly without jumps. This plot tracks the curvature derivative. The absence of infinite spikes confirms the control signals remain bounded. Because of this, the arcs are dynamically feasible. The robot maintains forward velocity through turns without impossible demands on its steering actuators. A route that optimally avoids obstacles on paper fails in reality unless C2 continuity constrains the physical forces demanded of the hardware. Once the continuous trajectory is generated, the motion controller takes over to drive the robot along it. To evaluate performance, we test two distinct controllers, a reactive PID and a model predictive controller, or MPC, on a linear point mass model that moves equally well in any direction. This overlay tracks the result. The red MPC trajectory perfectly hugs the green reference line through the curves. In contrast, the blue PID line heavily oscillates, consistently overshooting the target path. Looking at the tracking error over time confirms the visual data. The red MPC error stays tightly bound around the zero line, while the reactive PID drifts by up to 2 full meters in the x direction. The MPC achieves this precision through its prediction horizon. It continuously calculates the robot's future states, anticipating upcoming curves and adjusting its acceleration proactively, rather than reacting only after an error occurs. But this predictive capability carries a penalty. As the MPC solves for future states and applies sustained corrective forces to stay strictly on the line, its cumulative energy expenditure climbs significantly higher than the PID's alternating on-off corrections. For linear dynamic models, the MPC operates as a multiple input, multiple output system. It simultaneously solves for the x and y velocities, maximizing tracking accuracy by handling the coupled state variables together. Predictive control buys near-perfect tracking accuracy, but strictly at the expense of computational overhead and battery power. Those conclusions, however, completely invert when we switch the simulation from a point mass to a non-holonomic unicycle model, like a typical two-wheeled robot that has to rotate before it can drive forward. This layout examines unicycle dynamics. In the top left panel, the MPC trajectory entirely deviates from the smooth reference. The cross-track error graph shows a massive, sustained spike for the MPC, while PID maintains a near-zero error rate. The velocity profile further down reveals the exact failure. The MPC solver registers a zero mean velocity. It mathematically failed to generate a moving solution for the robot. This exposes a severe limitation. Unconstrained linear time-varying MPC assumes the physics of the robot behave linearly near the reference path. But unicycle dynamics, where steering directly impacts forward speed, are highly nonlinear. As the unicycle icon hits a high curvature turn, the actual physical state deviates from the linear assumption. The linearization matrix becomes increasingly inaccurate, and the quadratic programming solver breaks down, resulting in trivial or stalled inputs. The older, simpler PID architecture succeeds in this exact scenario because it uses the exact nonlinear trigonometric heading error, the arctangent 2 function, to drive its steering corrections, ignoring fragile linear predictions entirely. Adding computational complexity is a severe liability if the kinematic realities of the machine violate the algorithmic solver's underlying mathematical assumptions. These final simulations show the complete synthesized pipeline operating successfully in dense environments. The initial search routes are smooth to physical feasibility, and the controller correctly bounds the acceleration and velocity kinematics within the machine's strict mechanical limits. Integrating a memory retrieval system and B-spline interpolation yields a 9.3 times planning speedup and drops tracking errors by nearly half compared to standard baseline systems. High-performance autonomous navigation demands total integration. You cannot optimize a discrete path plan in isolation without accounting for the continuous motion controller that has to drive it. While predictive optimization delivers unparalleled precision for linear machines, deploying those same algorithms on nonlinear robots requires rigorous, constrained mathematical solvers to prevent systemic failure. Ultimately, highly theoretical optimization algorithms must always be architected around the physical, kinematic constraints of the machine executing them.